so I will not be apologizing too much. Besides, another reason to give it is that it is something that I wanted to present in my series of lectures in January and certainly didn't have time to do this. And returning to Dobrushin's rule that Ilya just presented, that let me present this new result while still like it, I will put software restrictions on myself. I want to present the result while it's still correct. Even if I don't like it. Okay, so I will be talking about periodic operators, and you have seen a lot of them even at this workshop, which should be more than about periodic operators, but still let me say a few words. You can consider as a model Schrödinger operator in Rn with Zn periodic potential. In fact, as I will mention a little bit later, it doesn't matter more or less what kind of operator you have, as long as it is elliptic in some sense and periodic. And as I will mention later, you can even deal with holomorphic, with d-bar equations, with equations on graphs, etc., in one shot. But this is a good example to have in mind. And then, as always, we introduce the Bloch Hamiltonian, which this is, since minus delta is d squared, where d is 1 over I gradient. Here we have d shifted by k plus v of x. And this operator is considered on the torus, on periodic functions. Oh, okay. You know what I meant. Okay, then it defines, since as we've heard many times, each of those operators has discrete spectrum. What you do, you draw the graph. Here is multi-dimensional quasi-momentum, and here is the spectral parameter. You draw the graphs of those lambdas, which is called dispersion relation, and they can collide, they can have all kinds of singularities and all this nasty stuff. What I need to remind you is that the spectrum of the original operator is just the range of this. You can consider lambda of k the spectrum of h of k as multiple valued function of k. And the range of this function is the spectrum of our original operator. So if you project those bands onto the spectral axis, you will get the spectrum, something like this, which correspondingly has band gap structure. So what I will be talking about is concerning what Bierman and Suslina called threshold effects, namely effects, various effects that depend only upon behavior of dispersion relation at the band edge. In the simplest case, and much better studied, at the bottom of the spectrum. For instance, for such an operator, the bottom of the spectrum will always look parabolic. And this is all the result by Kirsch and Simon. But other band edges, other spectral edges, could look much more complicated. But there are many issues which depend only upon the infinitesimal structure of dispersion relations here. And in many cases, not only infinitesimal, since due to analyticity, infinitesimal knowledge of this dispersion curve essentially defines the whole thing. due to analyticity. But in many cases, as I will remind you, even some finite part of Taylor expansion of the dispersion curve might give you the answers. Now, before I go any further, let me tell you in what generality everything I will be discussing works. So if you look at Rn as a covering over the torus, so here is the n-dimensional torus, here is Rn, and this covering is the group Zn. And our operator is periodic. We have a periodic operator on this covering. It's periodic in the sense that it can be pushed down to the torus. It's lift from operator in the torus. Now, essentially everything can be done in much more general situation, which is actually not a trivial observation, since you can do in one shot many things apparently not very much related. So you can imagine the same thing will be applicable to the situation when you have a manifold M, which is d-dimensional. It's covering of a compact manifold N, also d-dimensional, and the covering group is Zn. Now notice that unlike the situation in standard like periodic Schrödinger, when the rank of the covering group and the dimension of the space are the same, here the dimensions might be different. For instance, you can have Z3 covering a graph, which is zero-dimensional. Or the other way around, you can have a 1,000-dimensional manifold with a covering which is Z3 covering. And as we will see, many of threshold properties don't actually know about the dimension of your manifold. It will only know about the rank of the group. And it corresponds to Gromov's idea that if you look at a covering from afar, you don't see the covering, only see the deck group. And it's exactly what we call homogenization, by the way. Only in homogenization, as far as I have seen, people don't look at the cases when small details have a dimension different from the periodicity. Well, sometimes they do if you have discrete problem, but I've never seen multi-dimensional manifold with low-dimensional grid, which is possible. Okay. First of all, a couple of general words, that the things that kind of everyone knows, but as many things that everyone knows, it's hard to justify. The general understanding is that after what is called Flaquet and all those names transform, I prefer not to use the names of people who are still alive or very alive recently. Since there are so many, I don't want to get in between. So I call Flaquet transform, which is analog of Fourier transform. So after Flaquet transform, essentially what you reduce the operator to multiplication by a symbol, which is unfortunately or fortunately, it's multiple valued function. So essentially, operator should behave like kind of pseudo-differential operator with multiple valued symbol. Now, if we have a piece of dispersion curve and you are interested in behavior near some value of energy lambda, in physics usually this is what we call Fermi energy. Then the general idea is that if you have a wave package, namely some combination of Bloch waves, periodic times exponential, that correspond neighborhood of the spectral parameter and localized only also in K, some wave package kind of localized on this little piece of dispersion relation, then you expect that at least for some time, if you look at the picture with respect to time, if you look, for instance, at Schrödinger, non-stationary Schrödinger equation, this packet for a little bit, at least for some time, will feel like under the influence of the operator whose dispersion curve is this. For instance, in this case, it would be like a linear function, which would mean pure ballistic transport. If you are here, and this is the situation, for instance, in metals, although it's not nearly as simple as I said, since you have to look at the whole level set of dispersion relation, and it could be very complicated. It's called Fermi surface, and if you look at the book, there are whole books or websites with lists of Fermi surfaces of metals. You will be scared how complicated they can be. However, there are simple cases of interest, for instance, in solid state physics, when you study semiconductors, when this Fermi level is at the spectral edge. Then the general wisdom is that if the spectral edge is an isolated non-degenerated extremum, non-generated and degenerated in the sense that Hessian is not degenerate, then essentially those wave packets should feel themselves like moving in the free space, since this is a parabolic shape, and parabolic shape is exactly the shape of free Laplacian dispersion curve. And so for a little bit, they will feel like free electrons, except that this parabolic shape doesn't have to be isotropic. It is not necessarily round. It could have different axes, which corresponds to the fact that you have to introduce different masses, so-called effective masses, in different directions. But it relies upon the assumption that this is a parabolic shape. And yesterday, Sternberg discussed a lot this issue, which is, everyone knows that it is true, but no one can prove it, that generically, if you vary potentials or other parameters, if you are in optics, like refraction coefficient, if you vary, you can always achieve an isolated non-degenerate extremum. It's not known. Everyone knows that it should be true, but proving it is hard. Then another example, more recent example, sometimes your dispersion curve has conical singularities, like this. And if your Fermi energy happens to be here, then the wave packets here feel like they are under the rule of an operator whose dispersion curve is just, this is not true cone, it's just infinitesimal cone, it gets distorted first. So they feel like they are under the influence of operator which has conical dispersion curve. And this operator is well known. It would be two-dimensional massless Dirac operator. And that's why graphene, which you have all heard about, especially in the UK, where this exactly happens, that's why it has this terrific conductance. Since electrons kind of feel like they have almost no mass. Okay. So this is a general kind of wisdom that if you are near certain location and dispersion curve, if you understand what happens on this level, it will give you answers to many questions. So what I will do, instead of talking just about Green's function as I announced, I will give you a little bit of overview of different things related to this. I already mentioned effective masses, which have been, I think, at least from 1930s, if not earlier. This is the more recent stuff.
You are not saying that the Dirac cone can appear for Schrödinger with the periodic potential, right?
They can. They can. Actually, there is There are, by the way, it's a good question since I give you some references. First of all, conical singularities can appear very much anywhere. However, normally the general wisdom is that if you perturb a little bit the operators, they will split. And so they are unstable, and therefore, I will answer exactly your question. That therefore, you lose this, and everything which is unstable, usually you don't see it.
So you can write down particular v of x, right?
What?
So you can write down, you can give us particular potential, right? V of x.
Oh, this is very easy. I will give you the answer. So, what is special about graphene? That there is some special symmetry in the crystal structure which prevents you from breaking this cone. In presence of this symmetry, and the symmetry is just honeycomb symmetry. If you have honeycomb lattice, it has various, certainly it has shift symmetries, it's periodic, but also it has mirror symmetries, it has rotation symmetries, and it was noticed in 40s in some physics papers that if you do tight binding model, which means you consider discrete operator on this thing, it forces appearance of those cones. They have to be there. Then we, in 2000, I don't remember what year, we did this with Olaf Post for quantum graph models like this, which the difference is that in quantum graph, in discrete model, you have very few degrees of freedom. You can only change a number per vertex or maybe per edge. So there is not much freedom. Maybe this is why you cannot break the thing. But in quantum graph models, you have complete freedom of periodic potentials along the edges as long as they respect the symmetry. And we also proved this. And recently, Pfefferman and Weinstein, and this is Z. Pfefferman, Charles Pfefferman, and Michael Weinstein, they proved that if you have in 2D periodic potential which respects all honeycomb symmetries, it has to have those direct. So cook up any periodic potential that respects honeycomb symmetries and you will have those. Moreover, if you break the symmetry but not too much, for some time those cones also survive. It's very difficult paper to read since they introduced all the techniques of periodic equations, including Floquet transform and various properties. If you strip away all this very well-known thing, it boils down to a much simpler situation, and I recommend you to look at the recent preprint by Berkalaik and Komich, where, as it should be, they derive those presence of those Dirac cones under honeycomb symmetry without actually any difficult work. It's all about two things. One is representation theory, some simple representation theory, and another is some topological quantities like Berry phase. And it's all well explained there. And this paper is applicable to anything, to Schrödinger operator, to discrete, to quantum, anything that has this symmetry.
Dimension 2 is it, right?
Yeah, it's dimension 2. However, the science is not finished there, since we have examples. For instance, one of them we studied with one of my students, where you have much less than honeycomb symmetry to start with, and you still have Dirac cones that are stable. So it's not the end of the story, but this is not what I wanted to concentrate on. I do recommend you to look into these papers there.
Actually, just one short question. When you say it happens everywhere, every time, do you mean that, for example, on a combinatorial or quantum graph, you can, well, let's say a combinatorial, you can take an operator of any order, not
what I mean is that if you change parameters of the operator, this dispersion curve goes back and forth, deforms, those things collide, and when they collide, sometimes cones should appear. I don't believe that but the thing is that it's not generic. It's unstable, and therefore you don't see those things in practice. But if you have something that forces them to keep existing, like in graphene, then you can use it. Okay, so this is the example of when people apply in rigorous ways these ideologies that if you are near some point, if you know what is local geometry here, you might tell a lot about the behavior. Now, another example that you all know is homogenization. Homogenization actually deals with the following. So you have, if you take Schrödinger operator, as I said, the bottom of the spectrum always looks parabolic. That's Kirsch-Simon claim. Although if you allow magnetic potentials, it might not be true anymore, but without it, it's true. And what homogenization does, it looks at very long waves, and therefore at very low frequencies. And essentially what you are doing, you are looking at the behavior of packets in this neighborhood. While long waves, say, actually you don't consider longer waves, instead you shrink your environment. You make the coefficients oscillating faster and faster. It's the same as looking at this terrain with long waves. And then the result is that if you take the Hessian of this parabola at that point, it gives you constant coefficient operator, which is exactly what is called the homogenized operator. So homogenization theory is about this. Then it would be kind of natural to expect some homogenization theory not at the bottom of the spectrum, but at the band edges. And this is what Biermann and Suslina did, I think, I don't remember, 2006 or whatever, in several papers several years ago. They introduced some kind of homogenization here. So this is also threshold effect, and here it depends only on the, you don't need the whole germ of this thing. You only need to know the jet of order 2, in other words, only Taylor polynomial of degree 2 at this point. You don't need to know anything else.
Because as you said, right, for the bottom of the spectrum, quadratic behavior is a general fact which could be shown, but for the higher lambda, this has to be assumed.
For higher lambda, it's not general fact, it's not generally true. It should be generically true, and this is always true if you have electric Schrödinger. Since it's always true, it's easier to establish. Essentially, the proof is based on the fact that the ground state doesn't change size. Okay, this is another example. Now I will give you an example which actually contains some of our recent results, and I hope to have some time to tell you some other interesting stories. What else depends on those local structures? What happens that if you look at Green's function of your operator, then, for instance, you are inside of a gap. This is a gap in the spectrum, and you're somewhere here, and you look at Green's function, which is the kernel of the resolvent. It's a very standard thing to obtain estimates depending on the distance to the spectrum, and it gives you exponential decay of Green's function. The further away from the spectrum you are, the faster it decays. And there are many works about this. For instance, there is the well-known Thomas estimate. Then I think Barbaro and Kuchment and Peter Hislop improved on this, etc. What the issue is the following: that if you look at Green's function as functions of x and y, those operator methods tell you that it decays, it has some decay, exponential decay when x and y go far apart. However, this decay, you will get the same constant in any direction. But this is not the true thing. The decay of Green's function here will not be the same as with the same exponential rate in all directions. The accurate behavior should depend on the direction in which x minus y goes. So it should depend on the unit vector x minus y over x. And standard operator methods don't do this. Another thing is that if you look at Laplace operator, just Laplace operator, it has this dispersion curve, just a k squared. And if you look below the spectrum, it's explicit calculation done in textbooks. You will see that Green's function not only decays exponentially, it will be isotropic since Laplace is kind of round. But you will see that there is additional polynomial decay, which you don't catch with standard operator techniques. So the idea is that if you are near edge or internal edge of the spectrum, and if this edge is parabolic, and we assume it's generic, it's not proven, but we assume, you should have Green's function estimates for your operator, for instance, for Schrödinger, that should be more precise than the general ones from operator estimates. Namely, they should catch this correct exponential behavior in different directions, and it should provide additional polynomial decay. And this happens to be true. So I will give you now the results, the recent results about this. So they are so far correct. If you ask me why it is needed, I will not answer firmly, but I think that it should be useful whenever you perturb periodic operator either by localized perturbations or by random perturbations. So it has to be related. This precise asymptotics of Green's function might be helpful there. But if not, who cares? It's an interesting question anyway. That's the only judgment of correctness in science. Okay, so let me give you, first of all, before I do this, I can tell that below the bottom of the spectrum of operator like this, and even you can add drift to this operator, and you can add variable coefficients. This has been studied by people before. First of all, by Martin Babillot. Frederick, I don't know, I think that she passed away. Yeah. Then it was in around 88. You can find discrete versions. She did this for actual, it's related to studying Martin boundaries. And that's why she was a probabilist. And then you can look at the book by Voss, Random Walks on Graphs. At the end, he provides both cases at the lower edge and below it for Green's function. And Murata and Tsushida also did this somewhere, 2000, somewhere after 2000 maybe 6 or something. I don't quite understand why, since Babillot did this before. But it was very hard to read her papers. Okay, so I will be only concerned about internal edge. And the techniques used below the spectrum are not applicable, since they are mostly based on positivity of Green's functions and the other. It's not applicable. So I will just give you the results. Two results. One about the behavior at the edge, and another behavior in the gap near the edge. So if you are at the edge of the spectrum, and let's say K naught is a quasi-momentum where it occurs, and I assume that it is the extremum is attained only by one band function, and Klopp and Ralston proved that this is generic situation, but I also assume that it's isolated and non-degenerate, so Hessian is non-degenerate. Then, for the Green's function, you have the following asymptotics. First of all, some ugly coefficient which contains some numerical things and contains determinant of the Hessian at this point. So Hessian of what? So we have, let's say, lambda of K is the branch that we are studying, this branch. And we take Hessian at this extremum point. So then there is some coefficient. If you insist, I can write it, but it's not very illuminating. So first of all, this is done only for dimensions 3 and higher. If you have dealt with those things, you know that things get hairier and different in dimension 2 if you're at the edge. So for dimension 3 and higher, so here is and I will explain everything. And this is all times 1 plus O capital of x minus y to the power minus 1. So the principal term is this. There's an explicit coefficient involving
Sure, you didn't mean put exponential decay there.
what? There is not exponential decay. We are at the edge.
You at the edge, he's
sorry,
not
at the edge.
outside the spectrum.
At the edge.
So this is actually not, I would say, not related to Kuchment, because Kuchment have to be
Yes,
out.
it is. But I will give you, and this is somehow easier thing to do. It's easier to do this at the edge. And what is h of x minus y? It's square of the norm of x minus y determined by the Hessian h. It's quadratic form of the Hessian of x minus y. And if you look at this, you will see that this is the correct exponent. It's, since this is kind of square of the distance, this is n minus 2, which is exactly what you have for a Laplacian at the edge in dimensions 3 and higher. And
How does it divide? It's a limit procedure, right? You go to the resolving set.
yeah.
Because
Oh, I didn't say what these guys are.
no, but the h.
What?
I mean, h is the Hessian of lambda k at k naught.
At k naught, and it defines your new norm. This is the square of this Hessian norm of x minus y. It's hx minus y dot x minus y. If you are near the edge, then the idea is that if you are near the edge, you are inside of the spectrum, but near the edge, the dispersion curve, you don't hit the dispersion curve here, but somewhere in complex domain you will hit it. So the exponential decay will come from how far in complex domain you can go. So what you do, you actually write the Green's function formula. Oh, again, I didn't say what these were. This is the periodic part of the Bloch eigenfunction at this point. This Bloch eigenfunction has exponential part and periodic. Now, if you go, if you are near the edge, here is approximate picture what happens. This is your point K naught, and this is a complex domain. You don't see dispersion relation here, but it is big analytic variety everywhere else. So if you go, oh, this is imaginary quasi-momentum, this is real quasi-momentum. If you go in the imaginary domain, eventually you will hit this dispersion curve. But the thing is that if you go in different dimensions, you hit it at different times. So what you do, you draw a vector S, unit vector S, which is in my case x minus y over absolute value x minus y, and you look how far you go till you hit the dispersion, and this is beta S. Then in those notations I can give you an answer. I will drop even worse factor, but it's all explicitly written.
Is inside, so which actually means that Green's function is equal to 0 at zeros of this phi.
Of what? Yeah, Green's function oscillates.
Okay.
Green's function doesn't preserve the sign there.
Maybe similar. So basically, this contribution comes from when you throw away everything except one.
Yes,
momentum.
yes, that's what I was.
That's what related to Roman's question. I would guess that at the points where the function vanishes, you have to take into account the next one, or is it just enters through this O?
Oh, yeah, I see whether this O is multiplied by that. That's a good question. I didn't look into the paper. It was, by the way, I didn't mention it was. This is joint work. This was joint work with Andy Reich. I think it is multiplicative.
Okay.
Andy Reich in mathematical Nachrichten. Probably in 2012 or something. And this is what I will be talking now. It's joint work with Minha, my graduate students. Andy Reich is at the University of Arkansas, and also Andy Reich and myself.
But you are taking lambda k in the spectrum, in this one.
Now, no, in the gap.
Outside.
You can go into the spectrum. Then you will be dealing with a limit absorption principle, and people were doing this.
No, but the other one is in the spectrum.
That's
The
it.
one on top.
Exactly.
The one on top is in the spectrum.
Yes, it's at the edge.
At the edge.
It's non-degenerate
But
edge.
outside. So what is lambda k here? You wrote lambda k. That's what confused.
So, lambda of k exists everywhere. It's a function of k in complex domain. You don't have it if you are not in the spectrum, but when you go to complex domain, you will hit it eventually. So then up to some coefficients, and here we will not have multiplicative thing, and actually the estimate of the error will be worse. We have the following, some coefficients that will define k naught and this direction s, and then we have e to the power x minus y, ik, should be minus, I think, beta s. This is where we hit in the imaginary direction. And so we have both oscillation and decay. And here we have things like also some quadratic form. In this dimension, and here we have phi k naught plus I beta s of x, phi k naught minus I beta s y conjugate, and essentially, and the inner product of those two. And then there is an error with of the following form. We have the same x minus y minus x minus y beta s, like here's the same decay, plus an error which is O of x minus y minus n over 2 plus epsilon. So it's worth estimate, and here I need to make the fair disclosure, and you might suspect something here. Since you see these two functions are, you don't have eigenfunction right here, but when you hit the complex, you do. You need both this eigenfunction and the opposite side. And why would you hit them both at the same distance? And this is where we're somewhat stuck. We can do this only when this extremum occurs at one of the high symmetry points in Brillouin zone, which is, well, constantly assumed in physics literature, but we had a paper where we showed that it's not correct assumptions, that extrema can happen somewhere deep inside of the Brillouin zone, and something should be possible to do there, but we have not succeeded yet. And a couple of words, so you correctly mentioned how you can do this. If you look at the papers, one is like 40 pages, the next one like 50, but that's why I decided not to tell any details, since for initiated, most of it is obvious. But you have to write it down anyway. For non-initiated, it will kill unnecessarily. So the whole idea is, first of all, so you cut things off. First of all, you cut off all other branches of lambdas. Trivial estimate shows that it contributes very fast decaying terms. Then the remaining band function, you cut away everything except small neighborhood. And this accounts for all those phi k's, etc. That's clearly projector, spectral projector. And what remains is a scalar integral, almost the same as for a Laplace operator. And most of the difficulties are with this scalar. It's ridiculous, but at least for us, this was the most difficult thing. For instance, at the band edge, we know that's the integral you get for Laplacian. Now you have some term which is O capital of k cubed, and the whole battle is to show that you can throw away this thing without hurting the result. It looks ridiculously complicated. It should be simple, but we don't know simple way of doing this. And the same thing inside of the gap, but worse, since now we need to know the geometry of this dispersion curve in complex neighborhood. If you don't go too far from the spectrum, it's not very complicated. So this is how it is done. Well, and it's correct question. I am concerned it might be that on one of the steps of throwing away, we might have missed additional additive O. It might be. I cannot guarantee this. And then I wanted to tell you another story which is not brand new, but I think it's interesting. By the way, although we didn't do this in this paper, and there are some complications there, but they are all, I'm sure, manageable, and my student Minha is essentially practically done with this. You can do this on coverings, on abelian coverings. And what is interesting, that your Green's function behavior will not care about the dimension of your manifold. It will only care about the covering group.
That would mean absolute value of x minus y, right? Otherwise,
Absolute value x minus y.
yeah, okay. On top,
Here?
on top, above.
No.
Don't you have exponential decay?
Yes.
Beta.
The beta s,
Yeah.
but the beta s change sign if x and y change sign.
Yes.
Yeah. That's why we have those two guys.
What change sign? Wait. So,
The S
okay, so maybe I don't.
S is x minus y over x minus y length. Now beta S
Okay.
is if you go in this direction when you hit. If you go in the opposite direction, you hit in the. Okay. So
Sorry, essentially you are saying, and as expected, however tricky this formula looks, this is must be just identical to the one when you take this quadratic geom, right, replace it by perfect parabola, right, with a constant.
except at the edge it's true,
Right.
but inside of the gap, this thing is anisotropic.
Right.
If you just take parabola, pure parabola, you have to take parabola which
Quadratic form with
Yeah.
anisotropic.
it's actually this thing.
In fact,
That's a very good question. So this thing needs to know not only the Taylor terms.
you refer to
It needs to know terms of higher degree as well. It needs to know the germ.
Right, since you refer to homogenization, this is quadratic form corresponding to homogenized operator, right? And which coefficients are expressed in terms
Yes,
this,
yes.
It is encoded, right? In
Yeah.
terms of eigenfunctions. I guess.
You can say so, but it's not actually homogenization since you are inside of the gap.
Peter, in the Baruch case of estimate, the presence of the other edge, if you are between the two, is felt in the estimate.
Since what we are doing, you see, the thing is that if you are in the internal gap, you can only do anything reasonable close to the edge. If you go further, you will go to, when you go to complex domain, all hell will break loose.
It's very local.
Yeah, it's only near, sufficiently close to the edge. There is no, I wouldn't even dare to try to understand throughout the gap, I don't know. And I wanted to give you another example. I think I started later, I have up to 10 minutes. I probably will need less. Another thing is about Liouville theorem. And this is a little bit older stuff. So this result was brand new done here, but this is the latest, the most contemporary edition was its work with Pinchover. The last was in, I believe, 2010. But since it fits into all those threshold effects, and it has some redeeming features in comparison with others, I will mention. So what is Liouville type theorem? Everyone knows Liouville theorems from complex analysis, probably from theory of harmonic functions, that if you have in Rn harmonic function which grows not faster than a polynomial, it is a polynomial. It is harmonic polynomial, and the dimension of those is exactly known. It is n. This is binomial coefficient. That's dimension of all solutions. So first of all, one thing is that they are polynomials. The main thing is that it's finite dimensional space for any n capital. Now, 40 years ago, S.T. Yao put forward the problem that if you have Laplace-Beltrami on a manifold of non-negative curvature, non-negative Ricci curvature, then this dimension of the space of polynomially growing solutions should be finite for any n capital. And he didn't ask about the formulas, there are estimates, etc. It was proven in, I believe, 96 by Koldin and Minikotzi. And Peter Lee had some partial results also. The work of Koldin and Minikotzi didn't actually necessarily need non-negative Ricci curvature. They had some weaker conditions, which, for instance, are satisfied if your manifold is covering of a compact manifold with a nilpotent group. And your operator, therefore, is Laplace-Beltrami is periodic. So then we started thinking whether we can do something like that when you have abelian group here. And especially it was interesting since in the beginning of 90s there were two wonderful papers, one by Moser and Struve, another by Avellaneda and Lin, where they proved the following, that if you have periodic divergence type operator like this, with periodic matrix function of x, then they proved that the spaces of all, for each n capital, the space of polynomially growing solutions is finite dimensional. Moreover, it has exactly the same dimension for the free as for the free Laplacian. They could even compute this dimension. So I wondered what does divergence form has to do with it, and whether I could do this something like that. They used homogenization techniques, which means that we are dealing with some threshold effect. And then I thought, what can we do for other band edges? And I had an idea. Moser said that it will not work. Unfortunately, he already passed away by the time it worked. But we studied the following thing. You have periodic elliptic operator on abelian cover, and you look at solutions of your equation. You might have the result covers simultaneously Riemannian manifolds with Laplace-Beltrami, or graphs with discrete Laplacians, or D-bar equations if manifolds are analytic. They're all done in one shot. And so what we discovered is that if you look at this equation, you can think that this is a spectral problem. I replace it 0 by 0 times u. It's a spectral problem at 0 eigenvalue level, which in most cases will not help you, replacing 0 by 0 times 5. But here it helps, since what we discovered is the following, that you have dispersion relation for your operator. You have dispersion relation for your operator.
L is H, right?
Oh, L is H. You know what I meant.
H is L.
Now we have dispersion curve of this for this operator, dispersion relation. And this is 0. Oh, I shouldn't have drawn it like this. 0 is here. I'm at 0 level. Now we look at the Fermi surface at this level. So we look at level set of dispersion curve at the level 0. First of all, the claim is that Liouville theorem holds if and only if. It's a very simple theorem. If and only if the Fermi surface consists of finitely many points. That's all. If it consists of infinitely many points, it is obvious since you have this infinite dimensional space of block solutions which are bounded. But if it's finitely many points, the Liouville theorem holds. Another thing which shows a simple, although no one mentioned this before. So you see, you say Liouville theorem means I give you n, and you say that the space of solutions of this growth n is finite dimensional. Could it be that it's finite dimensional for the growth like x to the power 5, but infinite dimensional for the growth of x to the power 1000? It wasn't discussed. Here you prove that all those things are finite dimensional simultaneously only. Then when do you have finitely many points in Liouville theorem? Here. It's threshold effect. So the claim is that, first of all, according to Klopp-Ralston, we can assume that only one band touches this level 0. Secondly, if the extreme is not isolated, we know the Liouville theorem doesn't hold. But if it's isolated, but I don't need degeneracy, we know the answer, that we know all the dimensions. And the answer is somewhat interesting. So what you do, you take lambda as k, you expand into Taylor series. Since this is a simple eigenvalue, it's analytic, you expand into Taylor series into homogeneous polynomials of degree L. Certainly this series starts from L equal 2. Lambda is 0, so it starts 0 level. Its critical points of derivatives drop, so it's essentially 2 and further. Now let's take L naught is the lowest degree for which this polynomial is not 0. I'm not saying non-degenerate, just not 0. For instance, L not equals 2 doesn't mean that it's non-degenerate extreme. It could be degenerate in some directions. The answer is the space of solutions has the following formula. So this is whatever, even if it's degenerate, it has some L naught. Otherwise, this analytic function would be constant. So this L naught gives you the space of solutions. And I didn't believe it when we proved it, since this essentially means that if you have one square or squares, the dimension will be the same. I started playing with constant coefficient operators, and I was surprised that it looks correct. Not only the proof looks correct, but the result also looks correct. What?
What about the operator that's just second derivative with respect to
That's a good question. Since if you, yes, I expected that someone will ask this. Since if you look at the second derivative with respect to x1 and the full Laplace operator, you will see that something is wrong. But the correct statement is the following. So if you take the homogenized operator, which has this symbol PL naught of D, it's constant coefficient operator, then dimension of solutions of gross order n capital of our original equation is equal to the dimension of polynomial solutions of this equation of this growth. If you say all solutions of this growth, then you will see that you're dead. one square and all squares, they give you different answers. The correct thing is that this homogeneous operator, you have to rephrase the question a little bit differently. You should look for already polynomial solutions of this growth. And then that's exactly the calculation I did. And so that's probably all I wanted to say. Oh, I think I went overboard.
Thank you very much. Any questions?
I can comment what looks intriguing, but it may or may not have something to do with some people call higher order homogenization, right? When you need to get like classical homogenization.
Like two-scale homogenization?
Yeah, you do two-scale, but you go to higher order terms in sort of.
Also, yeah, it should be related both to higher order homogenization and to scale homogenization. The regular homogenization cannot see internal edges of the spectrum. But two-scale, for instance, can. I am sure that it is true, but I haven't looked at it this way.
There are some kind of.
But Tanya, they did with Tanya Susan and Bierman, they did a lot of work on homogenization analogs near internal edges. So you should address the question to her. I'm not an expert.
But if you actually lambda of k, you try to approximate it not only by a quadratic thing, but try to look at cubic, full order, fifth.
Yes, I'm sure that you can get Green's function asymptotics for degenerate cases, but it will be such a hassle. I don't know. You need to be hard pressed to do this.
You have kind of separation of scale up to higher orders, and then you observe that those slowly varying fields they grow polynomially, right? It looks like it might be.
It might be. You're probably right, but I haven't looked at it.
Or comments or questions? Thank you very much.